tcp2+ made three major improvements that solved the congestion collapse problem the internet encountered. In the prior video, I talked about how it incorporated a congestion window into its two states of operation, slow start and congestion avoidance. In this video, I'll explain the other two mechanisms, RTT estimation and self-clocking. Recall that a TCP implementation boils down to three questions. The first is when you should send data. TCP's answer is to use a congestion window to limit its transmissions when the network is congested. Next, let's answer the second question. When should TCP retransmit data? It turns out that estimating retransmission timeouts well can have a significant effect on TCP's behavior. Choosing timeouts that are too long will cause TCP to stall, waiting for acknowledgements. Choosing timeouts that are too short will cause TCP to back off too aggressively, dropping into the slow start state. So tcp2+ introduced some improvements to timeout estimation. These improvements have turned out to be a generally good way to estimate noisy signals in network systems, so learning them can give guidance on designing other protocols. Since TCP transitions to the slow start state and retransmits on the timeout, having a good timeout value is critical. If the round trip time is a constant, then the optimal transmission timeout is just a tiny bit larger than the round trip time because a successfully received packet's acknowledgement should take an RTT after the packet transmission. But round trip times are not constant. They can be highly dynamic. Furthermore, they can vary significantly with load. As a flow sends segments faster, it might start filling queues along the route, increasing its RTT. Bursts of traffic from other sources can also vary the queuing delay. Given all of this noise, we need a robust way to estimate how long before assuming a packet was lost. Before tcp2+, TCP kept track of a single variable R, its RTT estimate. Each time it received a new acknowledgement, it would calculate an RTT estimate, M, from the time between when the segment was sent and the acknowledgement was received. R was an exponentially weighted moving average of those measurements. If there was no acknowledgement for a segment after 2R, TCP assumed it was lost and triggered a retransmission. So what's the problem with this approach? The basic problem is that it assumes that the variance of RTT measurements is a constant factor of its value. Imagine, for example, that you have a path with a high, low variance delay. For example, you have an underutilized link across the ocean floor. Even if the RTT is 80 milliseconds, with 99.99% of RTTs being between 80 and 81 milliseconds, this TCP algorithm would wait 160 milliseconds before triggering the retransmit timer. This is almost an entire wasted RTT. Or imagine the opposite case, where the average RTT is 20 milliseconds, but it has very high variance, such that RTTs are sometimes as high as 80 milliseconds. Despite the fact that a significant fraction of packets have a high RTT, TCP would assume these packets are lost, shrink its congestion window to 1, and retransmit them. So tcp2+ incorporates an estimate of the RTT variance in its retransmission timeout. It maintains an exponentially weighted moving average of the RTT estimates as before. It also measures how much the measurement differs from the estimate, that is, the error between the estimate and the most recent measurement. It applies an exponentially weighted moving average to this variance V as well. It calculates a timeout as the RTT estimate plus 4 times the variance. So if the connection is a very stable RTT, timeouts will be only slightly larger than the average RTT. But if there's large variation in the RTT, TCP will choose a much larger timeout. If a retransmission fails, that is, it isn't acknowledged, then TCP retransmits again with an exponentially increasing timer. TCP assumes that this means there's tremendous congestion, so continues its multiplicative decrease by increasing the interval between its retransmitted segments. The two values G and beta, they were selected after a bit of experimentation. This approach is reasonably robust to slight changes in them. There isn't any special magic behind them, they just tend to work well in practice. Here are two plots taken from the original TCP congestion control paper. They show both the RTT that TCP observes, the bottom light line with data points, and the timeout estimate TCP maintains, the dark line on top. TCP Tahoe, pre-Tahoe, was very conservative. The large gap between the measurements and the timeout value represent wasted time when TCP has been waiting too long to retransmit. Also, around packet 60, when the RTT spikes upward, pre-Tahoe would retransmit and slow start unnecessarily. In contrast, RTT estimation for TCP Tahoe, shown on the right, much more closely tracks the RTT values. So now we've answered the second question. When does TCP retransmit data? The lesson from this is that one needs to estimate a retransmission or retry timer. When one needs to estimate a retransmission or retry timer in a network protocol, consider not only the observed round trip time, but also its variant. So now we've come to the third question. When should TCP send acknowledgements? It turns out the answer is generally with as little delay as possible. If TCP follows this policy, it leads to a very important and powerful behavior called self-clocking. Self-clocking means that if TCP sends acknowledgements aggressively, then it turns out they will space out in time according to the throughput of the bottleneck link. The sender will receive acknowledgements spaced out over time. Since the sender will send new data as soon as the sender window advances, this means that it will send segments at the rate that the bottleneck link can support. This figure shows that behavior visually. The throughput of the network is shown as the width of the path, and time is shown as the length of the path. Packets sent on fat, high bandwidth links take a small amount of time. These same packets sent over a low bandwidth link have a longer transmission time and queuing delay, and so take more time. When they emerge out of a bottleneck link, they will be fast again, but spaced out in time according to the rate at which they exit the bottleneck. Since acknowledgement packets are small, and assuming the bottleneck is not on the reverse path, this means the acknowledgements will arrive at the sender at approximately the rate of which they traverse the bottleneck link. This policy has an additional benefit. TCP only puts new packets into the network when it receives an acknowledgement, that is, when one of its existing packets has left the network. From a congestion standpoint, this means TCP is keeping the number of outstanding packets, that is, the utilization of queues and capacity in the network, stable. So the self-clocking principle means that TCP sends acknowledgements aggressively as soon as it receives data segments. This is to signal to the sender that data has left the network, as well as to give RTT estimates and allow it to self-clock its transmissions. So in summary, TCP Tahoe introduced three major mechanisms that allow it to effectively manage congestion and obtain good performance even in busy networks. The first is that it introduces a congestion window and maintains an AMD-like state machine that transitions between the slow start and congestion avoidance states. This state machine controls how the congestion window updates. The second is that it calculates retransmission timers using both an exponentially weighted moving average as well as a variance, thereby reducing both false positives as well as false negatives. Finally, by sending acknowledgements aggressively, it self-clocks data transmissions to match the speed of the bottleneck link.